Okay, so this is a case study. So we're going to talk about application of machine learning towards the analysis of the CFI protein and trying to build a potential modification of the CFI protein in certain areas to improve the functional activity. So obviously CFI protein is a key element of the many pathways, and it plays one of the leading role in deficiency, sometimes to very chronic inflammation, which is obviously not good for many reasons, and complement the system disorders if there is a chronic inflammation process in place. So targeting that that protein is important. And so what we're going to look at that potentially introducing the mutation in certain aspect, which you can ideally should be able to learn from the data and machine learning. So how do we tackle that problem? So we're going to look at the particular situation when we are looking into complexes. So first of all, what was given to us is about 2,600 variants. So we for some of them, we have a screening data. So overall, we have AC50 data for the C3b complex, about 275 samples. So, and then for which we have a measured AC50 activity, and then we have about 400 samples measured AC50 activity when it comes to the complex of the C4b. So those are basically two different regulationary pathways we are looking at, and we are measuring the activity for two of them. So, and we'll show the results, what is happening when it comes to the data analysis for those two guys. So obviously there is an assay which monitors the activity and measure the data. So obviously we are not going to discuss here the experimental aspects of the measure. So we believe the measurement of the data was accurately enough. So obviously we have information about assay. We do have information about cofactor concentration. We know what is the substrate. We are looking, what is the substrate concentration. We know the concentration of the CFI itself, and some of the information, regarding the experimental design. So all this information was given to us. There are two ways to approach that problem. So obviously we have a data. From one point of view, we have a collection of sequences, and we have AC50. And then ideally what we would like, we would like to understand where do we need to introduce the mutation to increase the AC50 activity. So that's our primary goal and primary question. So there are two approaches we can take. Each of them has plus and minuses. So we can build a machine learning by using the frequency approach, meaning that we compute the frequencies of appearing certain all the amino acid in the sequence, right? And that would be input into the machine learning, and the outcome will be AC50. And we will just simply do the regression, or we can do the classification if we will bin the AC50 data into the bins. Or what we can do separately, we will introduce information about the structure, because the first approach, when you compute the frequency, you lose the information where that particular amino acid coming from. So you just basically count only it appears 20 times or it appears 30 times, but you don't preserve the information about the structure. Despite the fact that you can build the machine learning and make a very good prediction in terms of AC50, this approach loses the information about the structural aspect. And that's what I was trying to say you previously, that if you don't supply into the machine learning some additional information from which the machine learning can learn, there is no way you can get that for free later on. So in case identifying the structure without providing the structure wouldn't be possible. So therefore, there is an alternative approach where we keep the structure information in place, and we keep as well separation and coding of the amino acids. So that can be done via one-hot encoders, on which we're going to talk in a few slides, but that just give you an idea that we have a sequences and we have mutation in certain places, and for that mutations, it was a measured AC50. The question is now to come up with new mutations which will lead to much better AC50 concentration. So this is the approach if you would just use the frequency-based approach. So you do the simple regression model. As you can see that R square is not bad in that case. So about the 70% between actual value and predicted value. So from that point of view, obviously there are some kind of outliers, but not too many. But the bottom line, that majority is on a diagonal, and it's reflected in our square index, which is one of the indicators to measure the quality of the regression. So we didn't talk today about this, but that, I presume, all you familiar with this basic concept. So what we do in terms of the sequential based approach, we need to convert the sequences into the tensor. I already mentioned that this is one of the key steps to convert data into the tensor, and then do tensor operation and build high dimensional object which can be fitted into the machine learning. So how do we convert that information? So we're basically building the table which shows, for each of the sample, you have table of the length of the sequence, and then basically by 20, which shows there is a 20 amino acid, and in each of the position, if that amino acid is present in that location, you basically put 1, and everywhere else you put 0. So by doing these things, you kind of get that very so you see that colored blocks. By doing these things, you would have a very sparse representation of your sequence, where you're going to get a lot of zeros, and then you'll have some of the ones in some of the places, which will be basically correlated to position in the sequence, and then plus the type of amino acid you have at that position. And that's a table of 0 and 1s. That's already a rectangular matrix. That's a tensor. So obviously, we can operate with this tensor, and we can use that information, either integrated with some other information like concentration of the substrate and some other information, or we can just use it on its own. But that's a very important essential step. So now basically converting this data into the tensor structure. So that's what we end up having. So we end up having about 2,400 sequences. We have all converted them using the concept to one hot encoded, and we have some AC50 values. So which we are actually bin it because we don't want to do the regression, but we do binning them, is what we already discussed in the previous slide. Before do the binning, we've done the log transformed. Obviously, it's essential because you want to streamline the values and just look at the folds rather just magnitude itself, because we were interested in the increase of the activity by so many folds rather just being interested in concrete values, because it's not the whole point. We just want to differentiate it mutation which leads to the jump by 10, or we don't see any jump by 10, so things like that. So obviously, in terms of the neural network structure, we have the following configuration. We have input layer, we have a compression layer, so which we're going to talk a little bit about this. So we use here encoder, and I will show you in a sec how we decompress this one. And then we take the results of the compression layer, which goes into the several hidden layers. And then those are hidden layers then output our prediction, which is basically our bin index, where that sample will end up in terms of what would be the AC50 for that particular sample. So what is the compression layer? Compression layer is basically definitely utilizing the concept of an encoder decoder, and we talked a little bit about this. So what we've done, we compress all the tables, rectangular tables resulting from one hot encoding of the sequences into the low dimensional structure. So it's basically compressing to another table, but smaller table. Obviously, that smaller table is going to be not as sparse as the original one, so it's going to get a lot of numbers everywhere and less zeros. And the reason is just because it's a compression step. But the bottom line, it can be decompressed and reproduce roughly original input. That's the whole concept. And it's possible to train and implement this model. So this is how it looks like in terms of when you do compression and decompression. So you get, roughly the same results from the original matrix, but it's important to recognize that the dimension of the coarse one became 96 by 234. So this is our dimensions, whereas the original one was much higher, right? So we have very large dimensions, and we compressed to the low dimension matrix. So now we're going to use those compressed features as our input into the next level of machine learning, and we're going to use the deep neural network, which is one of the library exists in TensorFlow. You can basically train and use that concept and get decent configuration for your neural network structure. So as a result of this, obviously we were able to compare the frequency-based approach versus sequence-based approach, and we also implemented convolutional neural network as a comparison, obviously, because DNN model has been optimized and it has a much better implementation and connectivity between elements of DNN. It's overperforming the CNN, despite the fact that input was the same. We didn't spend too much time to optimize the convolutional neural network because we thought using already existing libraries better time spent versus, optimizing CNN ourselves. So we were able to build that model, and the accuracy as well. If you look at the sensitivity or F1 is really good. So you can see they're around 0.9. The area on the receiving operating curve was in the same ballpark, so it was like very competitive numbers. So we're all shooting around the same numbers, which is very encouraging and very convincing. So then, what is the next is basically a validation on blind tests. In a sense, we usually ask our client to keep some of the data not given to us, so we don't include that as a part of the training model, and then we can do the blind prediction. So this is a result of the activity. So the blind predictions using concept of prediction plus the error bar assigned to the predictions was really good, because we were able to capture a relatively good number of the cases without actually even looking at them. So it was really blind predictions after all. So the next step was actually looking to the SPD domain of CFI protein and then trying to find a residue which is responsible for mutations. And there are two approaches here. One is a biology-based approach. So we basically perform biology-based selection of residue to mutate, and then use the substitution matrix to mutate them and produce the list of the candidate. Or you can use the machine learning-based approach. You basically identify the position which more sensitive towards the mutation, and the most likely will produce changes in your AC50 activity, right? So we've done both. So then approach one, so we look at the 3D structure, we identify interesting domain, and we look at the potential combination around the residues the client knew about. So we just basically only add additional information by utilizing 3D structure of the protein. And by doing these things, we look at the distance matrix, and we identify then basically all the neighbors, which are the distance of the 7 angstrom, and then we use those positions to mutate using substitution matrix, and that's how we build the collections of different combinations. So again, this is a biologically based approach. Then machine learning based approach is that we need to identify basically variable, which is, if you perturbate this variable, it will result in changing your output. So our variable is actually a matrix, right? It's a big matrix, and it has a lot of position there. Which one of the squares you need to perturbate in order to see what would be the outcome, would it be changing or not? So what we've done here is basically the trick. So we first of all look at the sensitivity towards the coarse feature. So we basically look at the middle layer. We perturbated each of the component of the middle layer. That results in ability to monitor how would the output looks like. If it does change AC50, then we say that that particular location is sensitive, and then we see what is the trace of that location in the original matrix after decoding. And so obviously, if you look at that 4 black highlighted blocks up the places which is sensitive towards the perturbation and the final output, those are locations mapped back into the original multiple locations, right? But it still creates for you potentially the places to look for the mutations. When it comes to the machine learning, we didn't utilize any domain knowledge of biology. It's just purely network and mathematics. So we've done this analysis, identify the place, and that results in a set of the residual point where we believe the mutation of those locations will lead to change of the AC50 activity. So now, at this point, we still didn't know which one will increase, which will lead to increase or decrease, because what we just only know that those are position center. It was interesting to see that some of them, which is highlighted by colors, were actually known by our client. It's a proprietary data. They use that information, and they actually introduce the mutation around those points. But we also identify some other de novo residue, which nice to mutate and see what would be the outcome. Some of the new discoveries documented in the literature, and that actually leads to some of the deficiency and disease, but some of them are completely unknown, and maybe there is just artifact of machine learning, and they actually not so important, but maybe there is some interesting biology coming up if you mutate one of those new residue identified by deep learning and machine learning. So again, from the remaining part of the analysis, we still mutated, using the 3D structure of the protein, and we changed the amino acids around those residues using the 7 angstrom distance, and that's how we generated, a lot of mutated sequences, which we later on run it, through the machine learning to identify where they leads to increase of AC50, where they leads to decrease of AC50. And the bottom line is that, we managed to create about 100,000 of sequences, that potentially could lead to the increase of AC50 activity, with the probability belief assigned to them in terms of how confident we are believing in those predictions. And that has been passed to them client, and now they're really happy to see that list of libraries with a very interesting new location for the mutations.